Okay, so what I'm excited for is to tell you about this new place because we have a new lecture we're getting into. Um, this is not necessarily a hike per se because you can actually just drive right to it. But this is Calico Rock. I'm going to turn it sideways so you can see it a little better. The weather today honestly makes me think of this exact day that I took this picture. And it is, let's see, it is probably 2 hours north-ish of here. It's in Arkansas. And that's the White River that you're looking at. A lot of people go to the White River to like trout fish and stuff like that. Very beautiful. Calico Rock is not a big town. It's a very small town. North of like Mountain View. If you know where Mountain View is, it's really kind of a popular, famous, small town, famous city in Arkansas for like their music and like grassroots type stuff. And Calico Rock is north of that. So we like to come up here and you can drive really to this outlook, to this kind of rock cliff, and you can literally stand right there. And it's beautiful. And so it's a fun place if you're driving north, if you're driving to Branson or something to stop and see. However, my one warning is this: if you go there in the fall when the trees are changing colors and it's most beautiful, you have been warned that it is also tarantula mating season, okay, in Arkansas. I did not know this, and I do not like spiders at all, period. Like the itty bitty tiny ones I can handle, but I just don't do spiders. Like if there's a spider in the house, my husband kills it, okay? Whatever. And we have seen tarantulas every time we've gone. So just be warned, here it is. These are our friends and my husband, and they were all about getting close. I'm the one taking the photo, but I'm going to zoom in so you can just see. I can't even look at it. Oh, I can't even look at it. I'm going to zoom back out. Okay. So you will find them. Anybody that wants to hold tarantulas, I just don't know if we can be friends. I'm sorry. Sorry, another chat. If you okay. Alrighty. So it's beautiful, but there's the spiders. Okay, chapter 7. Chemical reactions, energy, rate, equilibrium. So we are going to cover chapter 7 and chapter 8, and that was what exam 3 will be on. In the past semesters, exam 3 was on chapter 7, 8, and 9. Usually I put 3 chapters to an exam. I'm trying something new this semester. We're just going to do chapter 7 and 8. Here's why. Chapter 7 is like a beast of a chapter, okay? I think what we're about to get into is the hardest, some of the most technical stuff in the course. I don't want to scare you. Don't be scared. It's just a lot. So that's why I'm shrinking down exam 3 a little bit, and exam 4 instead will be chapters 9 and 10. Okay, chapter 10 is another big chapter on acids and bases, but there's like 6 big topics in chapter 7 here that we're going to talk about. So give yourself some grace and some patience. Reach out to me if you need to. Don't wait because it's going to be a lot. And we're going to really start doing some of the nuts and bolts of it today. So I want to start talking about energy, all right? Because chemistry involves energy. And we really haven't talked about that a whole lot yet, but our bodies depend on energy. Lots of things depend on energy. As a society, we depend on energy. And so we need to understand this. And obviously, there can be some health implications when things with energy go awry. And that's exactly what this first photo shows. Anybody know what this is a picture of? By chance, slim chance, but somebody in the first lecture actually did. So this is the aftermath of a nuclear explosion. Okay, this was over in Russia, Chernobyl, Russia. The whole city had to be evacuated because of the amount of radiation that was released, as you can imagine. Back in the 40s and 50s, we started designing nuclear reactors and putting in nuclear reactors to use to power cities. To use nuclear energy that way. However, everybody was pumped about it until nuclear explosions started happening, which have much, much more damaging effects than other sources of energy, like burning coal, okay? So we kind of slowed down on the use of nuclear energy in our nation and globally, but we have since started to build better and safer reactors, and we've started using more nuclear power. So anyways, that is what you can see energy can do. Energy can be very damaging. Here's another, just a picture of a chemical reaction happening, and it's associated with the release of heat. So oftentimes when energy is involved, it can be in the form of heat being released or being absorbed. In fact, we learned back in chapter 1 that evidence of a chemical change was a temperature change, right? If something got hot or if something got cold, we said that was a chemical change. So chemical reactions are often associated with release of heat in ways as well. So talking about the human body and energy though, since we're going to be health professionals, you guys are going to be health professionals, we need to understand how energy relates to the human body. And so we're going to talk about this briefly, but then we're going to kind of get into some of the technical stuff. So what are some of the main forms of energy? Let's just kind of throw some of these around. Can anybody tell me one?
Kinetic
energy. That is definitely, kinetic and potential are like the two umbrella forms. We're actually going to talk about those in a slide or two down. Can anybody think of another kind? Heat. Okay, Bailey Phillips put heat. Bailey, I'm going to write thermal. I like that, but I'm just going to write it as the word thermal. Thermal energy. That's a kind of energy. Zoe said mechanical. Absolutely. Mechanical energy. Kenethia said chemical. Absolutely.
hydraulic dams. What is that called? Hydraulic?
What is it?
Like the water dams? What is that called?
Water dams are a source of potential energy, believe it or not, if we had to really classify it. Dams are holding back water, and as soon as you let that water go, and it has kinetic energy, but it's holding back, it's got tons and tons of potential energy. But yeah, they do use hydraulics and all kinds of things to help with dams. Gravitational energy. Dakota, I don't know if that gravity plays into effect more so with kinetic energy a lot of times. Like if something's falling and it has kinetic energy, it's because of gravity. Electrical, that's another one. Electrical energy. Just got excited. I felt like I was yelling. I think people outside can hear me. Electrical energy. So we've got thermal, mechanical, chemical, electrical. Okay, we talked about one. What kind of energy is in this picture? Oh, thank you, Kenethia. Nuclear. All right. Can you think of anything else? You have to kind of zoom out from Earth to think of another kind of energy. There's one more that I'm looking for, one main one.
Solar energy?
Yeah, solar energy. I don't know who said that, but good job. Solar, I'm going to write electromagnetic though, okay? But same thing. Electromagnetic or solar energy as well. Okay, so these are not all the forms, but there's some main forms of energy. And if we're talking about the human body, I'm going to ask this question down here. What kind of energy does our body use? If you're looking at these kinds of energy, which one do we give our bodies? Which one does our body run off of?
Chemical?
Yes, Hannah, chemical. Okay. We give our bodies predominantly two things. We give it food. Water is, I'm classifying water in that. We give it food and we give it air, oxygen. Okay. So those contain chemical energy. Food is essentially atoms, right? Carbon atoms and nitrogen, sulfur and oxygen, and different nutrients and things as well. Vitamins and proteins are all in there, but vitamins and proteins are made up of atoms bonded together. And so there is chemical energy all up in the bonds of food and air, oxygen that we breathe. So how does our body take the fuel? I put this little picture of this sports endurance nutrition because it says, fuel your body for optimum performance. And that's what we call the energy that we feed our body is fuel a lot of times. So how does our body take that chemical energy or the fuel that we give it, and how does it generate energy? Anybody know what processes do that for us?
Respiration?
Yeah, that's one way. Okay. When we respire, we breathe in oxygen, we breathe out CO2, and we generate energy from that. our body knows how to take that process. It's a lot of processes, a lot of steps in that, but knows how to generate energy. And I'm seeing in the comments, yes, digestion, which is essentially metabolism, and metabolism is the other way. Okay, so respiration is extracting energy from oxygen. Metabolism is how our body extracts energy from the breakdown of food. Hope you can read my handwriting. Okay, respiration is extracting energy from oxygen. Metabolism is extracting energy from the breakdown of food. And then Janelle mentioned this earlier, but we haven't talked yet directly about kinetic and potential energy. And we need to, because really the whole premise of what we're going to get into today hinges on the understanding of potential energy. So what is kinetic and potential energy? If we're just going to define it in very short terms here, what would you say? Kinetic energy is what?
In motion.
The energy of motion. Perfect. All right. What is potential energy?
Like waiting to move. Like, I don't know how to say that. Like it's like it could, but it's like saving up energy, like holding it.
It's not moving. Okay. The easiest. Anybody else have a thought? Another way to state what Aubrey was sharing? Energy at rest. I like that, actually. I've never heard that. But I'm instead going to write stored energy. Okay, so in just the simplest terms, this is how we can define kinetic and potential energy. Energy of motion or stored energy. What Janelle was talking about earlier with like dams on rivers, that is a ton of potential energy. Okay, we keep that in reserve in case we needed to run the water. If we had a generator or some other kind of energy source go out, we have dams in reserve so we can create energy that way. It's stored energy if we need it. Okay, so I want you guys to know potential energy, that is what happens in chemistry when we talk about chemical bonds. Chemical bonds contain potential energy, okay? I'm going to write that down. Chemical bonds contain potential energy. I'm going to abbreviate energy. That is where the energy is in a molecule or in a protein or in whatever, an ATP. You guys know ATP is the biological molecule of energy, right? The energy is stored in the bonds, and it is the breaking or the forming of the bonds that gives an energy transaction. So one thing I want you to get used to today, what you're going to see me doing, we are going to start writing energy into chemical equations as though it's a reactant and a product. And I want you to get comfortable with that. Here's what it will look like. We could say there's some reactions where energy is a product. So we would say energy plus our reactants. Did I say energy is not a product here? Sorry. There's some reactions where energy is another reactant. So we'd say energy plus our reactants gives us our products. And then there's other kinds of reactions where you have your reactants and they collide together and react and they give you your products. And they also produce energy. Okay? So I want you to get comfortable with us writing energy directly into the chemical reaction. Sometimes we may just write the word energy. Other times we may write a number with units of energy. What are the units of energy? Does anybody remember what units belong to energy?
Joules.
Joules or
Kilocalories.
Calories. Yeah, kilojoules, joules, kilocalories, calories. So sometimes we could even write, instead of energy, we could write, whatever number it is in kcals or kilojoules, okay? So just kind of get comfortable with that verbiage. All right, So let's actually get into some of the real content of chapter 7. How do we know if a chemical reaction will occur? I wanted to start with this broad question because we've been talking about chemical reactions. We've talked about how to balance and classify them, and then we've also looked at how to calculate certain things from them, like moles or number of molecules, mole ratios. But just because you can write a chemical reaction does not necessarily mean it will occur. Okay. In fact, I put this reaction on here right below as an example. We have AU and water in this chemical reaction. And what is AU? Anybody know?
Gold.
It's gold. Okay. Gold plus water. And you can make gold oxide and hydrogen. But I want you to think about this. If I have a gold ring and I just drop it into a cup of water, you think you'll see a reaction? No, right? At least not immediately. And so how do we know if a reaction will occur? Well, energy determines if a reaction will occur. And I'm going to put this word at the end of the sentence, determines if a reaction will occur spontaneously. Okay, spontaneously just means that once you get it going, it'll go and you don't have to do anything to it. But spontaneity, when it comes to chemical reactions, really determine if the reaction is favorable or unfavorable, okay? Favorable or unfavorable. Now, a spontaneous reaction, one that will occur once you get it going, is a favorable reaction. So instead of just spontaneously, I'm going to say will occur, or you could write or be favorable. All right. So energy determines if a reaction will occur spontaneously or if a reaction will be favorable or unfavorable. To expand on that thought just a little bit, the bullet point directly underneath explains a little bit more. If the products have less, there's our word, potential energy than the reactants, the reaction will occur spontaneously. If the products have less potential energy than the reactants, that reaction is a favorable reaction. All right, think about it this way. You know, we've talked about the octet rule and stuff in the past, and we say everything that happens with electrons and the octet rule, it's because atoms want to be stable. You guys remember us talking about that? They want to be stable, and a lot of them just inherently, where they're at, they're not quite as stable as they could be, so they'll trade electrons. It's the same idea here when it comes to stability. If your products have less potential energy, less energy in their bonds, they're more stable, okay? If you have less energy, I'm going to say less energy corresponds to, so I'm just going to put an equal sign or put a little squiggly equal sign, corresponds to more stability, okay? This totally falls in line if you just think about the closest 2-year-old you know, okay? My daughter's 2, and if she's had a ton of sugar, which gives her energy, she's crazy. She's gonna run around the house for an hour. But if she has less energy, maybe she's played at school all day or whatever, she comes home, she's a little more calm and a little more stable in our household, okay? Makes sense? You can apply that to chemicals as well. They have less energy, they're more stable. More energy, they're less stable. All right. However, I wish that energy was a very just simplified, reduced thing. It is not. And so that is why I say chapter 7 is some of the hardest, most technical stuff we get into, because not just one thing determines the energy of a chemical reaction. There's 3 things combined. And today we're only going to look at the first thing. The first thing is enthalpy. All right. That's what we're going to talk about today. And then next week, I'll introduce another term, entropy. And then lastly, we'll talk about temperature and how this plays an effect. All these things, we really, so hang tight in these next few days of lecture with me, because you're going to be wondering, what's the big picture here? What's the big picture? And I'm going to tell you the big picture is kind of this question that we started with. How do we know if a chemical reaction will occur? All right. Our bodies have to be able to answer that question very quickly. All right. Because all kinds of reactions are coming together to make our bodies function. But how do we know? Well, it's complicated. That's the answer. There's more than one thing at play here, so we have to understand each piece and then piece those things together to get the big picture, all right? So we're going to zoom in on the first piece, which is enthalpy. And before I define what enthalpy is, anybody heard that term, by the way, before? Maybe in a high school science class, or if it's brand new to you, I totally expected that, okay? I don't expect all of you to have known this term. So before I define it, I want to have a little conversation about bonds for just a second, chemical bonds. I'm going to read this statement here. Reactions occur via the rearranging of bonds. I'm going to read it again. Reactions occur via the rearranging of bonds. And you guys know this to be true. We have talked about the law of conservation of mass back when we talked about chapter 5, which says that when you have a chemical reaction, you're not creating sorry, there's a chat. Someone's having issues. Let me address this real quick. Zoom is only connection. Hold on just 1 second. Sorry, everyone. I'm sorry to pause the conversation. You know this to be true with the law of conservation of mass, which says when a reaction happens that we don't create or destroy atoms, we just rearrange them, okay? And so let's, for example, draw out a double displacement reaction, which is AB plus CD. AB plus CD, okay? And you guys know in a double displacement reaction, this is going to give us, we're gonna break apart and we're gonna get A, the cation, B, the anion. Then we're gonna break apart the other one. C is gonna be the cation, D is the anion, and these are gonna rearrange. And we're gonna get A, D plus the cation and the anion from the other compound, all right? We didn't create new atoms, we didn't destroy any, we just rearranged them. And it's the same idea with bonds, or energy rather. Okay, reactions occur via the rearranging of bonds, which is where the energy is. Now I'm gonna fill in these two blanks here. So the first one is that breaking bonds, that's an N, requires energy, and making bonds releases energy. Breaking bonds requires energy, making them releases energy. So let's look at this reaction that I just drew for a second, because I want to ask you a question. Which side of the reaction, the reactant side or the product side? On which side are we breaking bonds? Which side are you breaking bonds, the reactant or the product side?
Reactant side.
That's correct, the reactant side. Okay, over here we are breaking bonds. All right, and on the product side is where you're forming new bonds. So over here we are making bonds. So when we read these statements again, breaking bonds requires energy. What that means is on the reactant side, we have to invest energy. Okay, we have to invest energy to break the bonds, and on the product side, we will produce, or the word it's used over here is release energy. Produce, release, same idea. Okay, and this is always true. All right, now thinking about that, the next thing is, the next question that kind of arises from that is, well, how much energy are we talking here? Is it a lot of energy? Is it the same amounts of energy? And the answer is no. It varies widely. It depends what atoms are involved in the bonds. You guys know, we talked about ionic bonds and how different ionic compounds have different melting and boiling points, depending on how strong of an ionic bond's at play. So the answer is, it's actually not straightforward. It depends. It depends on what atoms are in the bond, and it depends on the number of bonds holding those atoms together. Okay, single, double, or triple. So the figure down here is kind of illustrating this point. If we have a molecule with a triple bond, okay, we know 2 nitrogen atoms are held together with a triple bond. Look at how much energy it takes to break those nitrogen atoms apart. 226 kcal per mole of nitrogen triple bonds. But if we have a molecule with a single bond, chlorine-chlorine atoms are held together with a single bond. It only takes 58 kcal per mole. All right, so that makes sense. Now this amount of energy We give it a name here because what we're doing is we're pulling atoms apart. So we call the amount of energy necessary to break bonds the bond dissociation energy. Okay, the amount of energy necessary to break atoms apart, to break bonds, is called the bond dissociation energy. You guys know what the word association means. If you associate with someone or a program, and the disassociation is the opposite of that, breaking apart, pulling apart. All right, questions so far on everything we just talked about, bonds forming, bond breaking, and how the energy transaction happens with that. All right. So this text is just the exact same from the slide above. All right. But it plays into this table. As scientists have studied different bonds between different atoms, they've come up with a whole tables and tables and tables of bond dissociation energy. So there's way, way more than just this table here. But this is the one in your textbook, and this is really the one we'll stick with. We won't, I'm not going to have you go look up random numbers on the internet for a different bond dissociation energy. So this table will be very handy. We're going to use it today, and you'll need it for the exam and quizzes and yada, yada, yada. So whoops, keep it handy. But I just wanted to point out how to read this table. You have 3 columns of different kinds of bonds. Okay, all kinds of bonds. Carbon-hydrogen bonds, carbon-oxygen bonds, oxygen-oxygen bonds, oxygen-nitrogen bonds, so on and so forth. Now this, again, does not represent all the bonds possible, but it's several. So it tells you what kind of bond and what atoms are involved in one column, and then it also tells you the bond dissociation energy in the next column, and it gives you 2 numbers. The first number is the kilocalorie per mole. That's how much energy in kilocalories. The second number is how much energy in kilojoules. And here's my one warning is do not accidentally do a problem. I'll show you the problems we're going to kind of do with this. With both units, either pick numbers from the kilocalorie column or pick them from the kilojoule column. Do not accidentally pick a number in kilocalories and then another number in kilojoules, okay? If you're going to do a problem, work it all in kilocalories or work it all in kilojoules. That way you don't get your answers messed up. So that's one thing about this table. The other thing is you notice there's an asterisk over here with the carbon-oxygen double bond. Why is that asterisk there? Well, normally the numbers for bond dissociation energy for a carbon-oxygen double bond are given here. 178 kilocalories, 745 kilojoules. But when the carbon-oxygen double bond is in a molecule of carbon dioxide, CO2, so let's draw one when it looks like this. When your carbon-oxygen double bonds are in CO2, specifically this molecule, the numbers are different. So the asterisk says, hey, come down here and read this. The CO double bond dissociation energies in CO2 are not the same numbers. Okay, so if you have a molecule of CO2 in a reaction, any combustion reaction, you need to make sure you use the numbers down here underneath the table to calculate bond dissociation energies in problems that have CO2. Okay, so just wanted to point that out. And in fact, look, a molecule of CO2 has 2 carbon-oxygen double bonds. So if you were doing it for the whole molecule, you would need to multiply these numbers by 2 because the molecule has 2 carbon-oxygen double bonds, right? Okay. All right, now I still have not even defined the term enthalpy yet, and I'm going to in just a second, I promise. Last thing I want to point out is this is the figure we were looking at earlier, and we said a triple bond requires way more energy and a single bond way less energy. I just also want to make the point that when you flip these reactions in reverse, when you take atoms and you bring them together and you form bonds, the same amount of energy is released. Okay, so this is the amount of energy that we had to invest to break these bonds, but when we take the atoms and we bring them together and we make the bonds, the same amount of energy is released. Okay, if we did these top reactions, I'm going to call this figure 1. If we did these in a test tube, the test tube would feel cold to us, okay, because it's absorbing energy. if we did these reactions, I'm going to call this figure 2 down here. If we did these in the test tube, these would feel hot, okay, because they're releasing energy in the form of heat, okay? All right, this, what we just talked about with figure 1 and figure 2 is summed up in actually a law, okay, a scientific law called the law of conservation of energy.
We can't see what you're running.
Oh man. Stop share, reshare. Can you now? All right, I just filled in that blank. The law of conservation of energy, which says, let me pull the chat back up. Which says that energy is not created or destroyed, it is just transferred, okay? In chemical reactions, it's just transferred from bonds, and it might be released into the surroundings, or it might be pulled from the surroundings and trapped in a bond. And then what I really was indicating with figure 1 and 2 here is that the energy required to break a bond is the, well, I need my pencil, the same or equal to the energy released in making that bond. Okay, questions. So we've talked a whole lot about bonds. We've talked about breaking bonds, forming bonds, and how energy is associated. Now let's actually define enthalpy, okay? So enthalpy, and we abbreviate enthalpy with an H. I don't know why, we just do. It is a measure of the energy stored in the reactants or the products, okay? Enthalpy is a measure of energy, and we know that potential energy in chemicals, it's stored in the bonds of the reactants and the products, all right? So all those bond dissociation energies, those are the enthalpies. Those are, you could also call them bond enthalpies. The bond dissociation energy, I'll even write that, I'll abbreviate. Bond dissociation energy, that's kind of the same, it's synonymous with saying bond enthalpies. Okay. So that's enthalpy. Now, when you have a chemical reaction, though, things are changing from reactant to product side. Things are changing. So we also need to know how to calculate and measure a change in enthalpy. And that is delta H. Delta H. Okay, Greek sign delta is in chemistry means change. So change in enthalpy is delta H. Plain old enthalpy is just H. And that is the difference between the energy needed for bond breaking, and then which is on the reactant side, and bond formation, which is on the product side. Okay. So I'm going to teach you how to calculate change in enthalpy today, and that's exactly what the dry lab is going to be over next week as well. So if you pay attention real quick for the next 20 minutes, you'll be set up in good form to do the lab for next week as well. So let's say we have this reaction here, nitrogen and hydrogen, and we're going to make ammonia, NH3. To look at how much energy we need to break all the bonds, we first have to figure out what kind of bonds we have, okay? And how do you figure out what kind of bonds you have unless you draw out the Lewis structure? So you thought you were done with Lewis structures, and you're not, okay? Don't forget how to draw out Lewis structures, okay? And everyone smiled and said, good, because you love Lewis structures. So let's draw the Lewis structure for nitrogen. It is a nitrogen-nitrogen triple bond. How many of these should I draw? How many nitrogen molecules? According to my balanced chemical reaction, how many should I draw? Yeah, just one, okay? So, and conveniently, I have put down here for us the bond dissociation energy for that nitrogen triple bond. We'll write it in just a second. Actually, we can go ahead and write it in now. So it's 226, I'm just gonna write it underneath, kcal per mole. And so that's how much energy we need to break that bond. Okay, we also have 3 hydrogen molecules. So I want you to draw out 3 hydrogen molecules. I'm going to draw them kind of small. Hydrogen is held together by a single bond, or 2 hydrogen atoms, I should say. So there's my, sorry, I'm going to pull this down a little bit. There's my 3 hydrogen single bonds, and I have put the bond dissociation energy for a single hydrogen bond down here. So what we're going to do, because we have 3 of them, we are going to say 3 times 104 kcal per mole. That's how much energy we would need to break all those hydrogen single bonds. Are y'all with me so far? Okay. Now total, to break all the bonds on our reactant side, we just need to add all this up. 226 plus 3 times 104. Can anybody do that for me? 312 and 226, that's 512. 532, 538. Is that what you got? All right. So it should be 538 kcal per mole. All right. On the product side, we have 2 molecules of ammonia, NH3. So we need to draw the Lewis structure for ammonia to see what kind of bonds and how many we have. And notice we're going to have to draw 2 of these. I'm just looking at my coefficient here in my balanced reaction. Ammonia is NH3, so it's nitrogen bonded to 3 hydrogens. And don't forget that nitrogen has a lone pair. I'm going to draw 2 of them. I'm going to draw the next one out to the side. All right, there's my 2 molecules of ammonia. Now, here's the question. What kind of bond do we have on the product side? It is a nitrogen-hydrogen single bond.
Oh.
Right?
Yeah.
Nitrogen-hydrogen single bond. And we have how many?
Would it be 6?
Total, we have 6. 3 from the first, the Lewis structure on the left, 3 from the Lewis structure on the right. So I have the bond dissociation energy for a nitrogen-hydrogen single bond, and we're going to multiply that by 6. So it'd be 6 times 93 kcal per mole. All right. And total, what does that give us on the product side? That's the only bonds we have, so we don't have to add anything else.
Where did you get 6 from?
6 came from, let's count them. We have these hydrogen, nitrogen single bonds. And here's 1, there's 2, there's 3, 4, 5, and 6.
Oh, okay, I see now. Okay, thank you.
Uh-huh. And I will tell you guys what we're doing. We're calculating change in enthalpy. We're going to wrap it up in a second, but none of this math is hard, right? It's not calculus. It's just can be technical. You have to make sure you get the right kinds of bonds and that you count them up right. And if you accidentally miss one, then your whole thing will be off. So that's where the technicality comes in here. Anybody, what's our answer for our product side? Y'all gonna make me do this? Okay, 6 times 100 is 600. Thank you, 558 kcal per mole. All right, so now to calculate delta H, the change in enthalpy, which is what this is all about, we are gonna take the enthalpy of the reactants and the products, so we're gonna find the difference. So I'm gonna tell you, here's our equation for delta H. It is this. It equals the enthalpy of the reactants total, the sum of that, minus the enthalpy, the sum total of the enthalpy of the products. Okay, and actually in your textbook, what you probably see is you see this symbol. What that symbol means is the sum. Okay, see how on the reactant side over here we had to sum up the total between the nitrogen and hydrogen. Just that E just means the sum of. So you're adding it all up on the reactant side and the product side, and that's how you calculate delta H. So if we do that, and in fact, I'm just going to, well, I need the space below this, so I'll write sum up above. So to do this, we're going to have delta H equals, it was 538 kcal per mole on the reactant side minus 558 kcal per mole on the product side. And the difference there, delta H, is negative 20 kcal per mole. That is how you calculate a delta H, a change in enthalpy, a change in the energy needed for bond breaking and bond forming across a chemical reaction. Okay, so here's the deal. You can do all this cool math, but what I want you to know, I want you to know how to do this, but I want you to know what it means even more than that. Okay, what the heck does this mean? So if we think about this, let's look at these numbers up here again. And in fact, I think if we scroll down, this right here is just the same stuff we already filled in up top up here, so you can ignore that. We just looked at how to solve for delta H. Here's kind of a summary of what we learned. We added up the enthalpy of the reactants. I'm just going to abbreviate that with an R. And the enthalpy of the products, right? And that's the numbers we got. So what this means is overall, we released more energy when we formed the bonds of ammonia, our product. We released more energy there than when we had to break all the bonds, than the amount of energy that we had to invest to break all the bonds on the reactant side. So overall, when heat is released, okay, we had an excess of 20 on the product side. And so that means our delta H is negative. Delta H is negative. Overall, when heat is released, which is what we see here, because this is a bigger number, enthalpy of the products is a bigger number. So overall, we have excess heat on the product side. So heat is being released, and that means delta H is negative. Now overall, when heat is absorbed, wait, A, BSR, is it B or P? I'm a terrible speller, if you haven't figured that out. Is that right? That doesn't look right.
It's a B instead of the P.
Thank you. My husband's the speller in our family, but he can't do math worth a flip. Delta H is positive. All right. Okay. Questions on that? I know this stuff is kind of abstract and it's hard to get a handle on, so we're going to practice it some more. We're going to do another equation, and maybe it'll sink in a little more after that, okay? All right, let's do another one. Let's look at this. We have this reaction with nitrogen gas and oxygen gas, and it makes 2 molecules of nitrogen monoxide, NO. And here, I'm not going to actually take the time to draw out the Lewis structures, although you typically will have to. On the lab next week, you will have to, because we already have the bond dissociation energies listed, and we just need to look at, there's only one kind of bond in each of these molecules, so we just need to look at the coefficients to know if we need to multiply them by anything before we add them up, all right? So we have coefficients of 1 on the reactant side, which means we don't have to multiply by anything. So all we're going to do is we're going to add these two numbers up. So 226 plus 119 is 330, 45. Is that right? Is that what y'all got? That's the amount of heat that we have to input to break all the bonds of our reactants so that the atoms can rearrange and give us our products. Now, when we make nitrogen monoxide, we release 151 kcal per mole. And we have 2 of them, though, so we're going to do 2 times that. And we should get 302. Okay. Now, what is our delta H? Okay, what is our delta H? If we do 345, remember it's the enthalpy of the reactants, so 345 kcal per mole minus 302 kcal per mole, we should get 43. And this time our delta H is positive. Okay. So what does it mean? I'm going to fill in this blank here. We had 43 kcal per mole. More energy was necessary for bond breaking. And remember, I'll scroll right back if you're in the middle of writing. Let me go up. Remember up here, where was it? Where was it? Right here. We said the reactant side is where we break the bonds. So if we had 43 kcal per mole more on the bond breaking side, that's on the reactant side. That makes sense because our heat input is the bigger number. All right, so we have 43 kcals per mole energy excess on the reactant side. So more energy was needed for bond breaking than what is released in bond formation. Overall, heat input is needed. All right. So how do we write this in? If we actually were to write this in into our reaction, remember I told you we're going to write energy into the reaction like a reactant or a product. When your heat input is bigger than your heat output, we're going to write energy in as a reactant. You can literally write the word energy, or you could write the number. And the number here is your delta H. You'll write in your delta H, which is 43 kcal per mole. So that amount of energy plus nitrogen molecule plus oxygen molecule will give us our products. Okay. Questions on what we just did and how we just wrote energy in. We actually didn't do this for the first reaction. Let's go back. Let's go back to the first reaction and write heat in. I want to know if we're going to write it in as a reactant or a product. So here was our first reaction. Nitrogen and hydrogen make ammonia. And remember, our delta H we calculated right here, -20. So should I write energy, or I could write -20 kcal per mole as a reactant or a product this time? Dakota, I'm about to answer your question in the chat. Do y'all think I should write it as a reactant or a product? When it was positive, we wrote it on the reactant side, but this time it's negative, which means, look at our two numbers. Okay, this is the heat input number on the reactant side. This was the heat output number on the product side. So if the heat output number is bigger, we should write it on the output side, the product side. And actually, when you write it in for the product side, this is unique to the product side, you drop the negative sign. You can just write it produces 20 kcal per mole of energy, okay? The fact that we write delta H as negative lets us know we should write it on the product side. But when you actually go to write it in, you just write the absolute value of it as a product. So Dakota, yes, if delta H is positive, you just write it in front of the reactant side. If delta H is negative, you write in energy or the number as on the product side. Okay, you guys have done a lot today. This is good stuff that we're doing. All right, so this is just kind of a summary recap of what we've talked about. When heat is released, delta H is negative. If it's absorbed in the reaction, delta H is positive. So I want to ask you this. This reaction right here, and put my box around it. If I did this in a test tube and I'm holding it in my hands, would the test tube get hot or cold to me and to you? What do you think? Caitlin says it would get hot. Hot. Angelina also agrees that it would get hot. Anybody disagree? Everybody thinks it would get hot? Well, think about this. This reaction is absorbing more energy than it is putting out, okay? That's what heat input means. It is absorbing more directly into the bonds than it is producing when it makes our products. What we feel is the production part. Okay, so if this reaction is actually absorbing more energy from the surroundings, what we are going to feel, because we're the surroundings, is an absence of heat, because that heat is now moved into the chemical bonds of the reaction. So this test tube would get cold. Okay, it's okay if you guessed wrong, at least you guessed. So, and a reaction where energy is on the reactant side, that test tube would get cold. Overall, the reaction is absorbing heat. And guess what? Up here, if we did this reaction in a test tube, that test tube would get hot because overall it's producing energy, and we would feel that production of energy is heat. Okay, I'm going to skip over this slide. I put this table down here just in case we needed it as we were calculating numbers, but I don't think we did. Now that we've learned how to, we've defined enthalpy, okay? We've looked at how energy is related to bond breaking and bond formation. And now I'm going to define two more little vocabulary words here. If heat is released, here's our two reactions that we did. This was number 1 and this was number 2. And here's the delta H's that we got. One was negative, one was positive. So let's look at this first one where delta H is negative. If heat is released and delta H is negative, we call that reaction. Anybody know what we call it? Anybody maybe can guess the word I'm about to say? What kind of reaction is that? One that gives off heat.
Something exothermic? Is it exothermic?
Who said exothermic? Yeah, it's called exothermic. Thank you. And can you type it? Exothermic. We call that an exothermic reaction. A reaction that gives off heat is an exothermic reaction. I want everybody to take your hand and put it on your forehead. Does your forehead feel warm to you a little bit? Usually, kind of? Yes or no? I don't know how your forehead feels. To me, it feels a little bit warm. It should, because we are all giant exothermic reactions, okay? We are exuding heat, whether we know it or not. So if you're giving off heat, you're exothermic. Well, on the flip side, if heat is absorbed and delta H is positive, the reaction is endothermic. Okay. All right, I have a poll question. I want to see how well we grasped this. So this next slide here, I have 4 reactions. I'm about to launch the poll, but go ahead and start looking at these reactions. I want to know, are they exothermic or endothermic based on the stuff we just talked about? So select your answers to all 4, and then we'll talk about them. Okay, 28 of 46 have voted. So that's not a lot. Go ahead and try to, even if you have to guess, we're going to talk about them. All right, almost there, 40, 46. Maybe we'll give it a couple more seconds. All right, maybe not. I'm going to end the poll. Seems to be all that is going to vote. Okay. So we have some different answers here across the board. Let's look at these. Can you guys see the results now? Let's talk about number 1. We have A plus 2B makes AB2 plus heat. Heat is a product here. Let's go up here and look at the definition of exothermic and endothermic. If heat is released and delta H is negative, I don't know if you remember, but when delta H was negative, we wrote in heat as a product, okay? Or we wrote energy. Energy is heat, heat is energy. So you can write heat or energy as the product. So if heat is a product, this is exothermic. 73% said exothermic, almost 30% said endothermic. All right. Now, beneath that, if you look carefully, we have A plus another B, 2D, whatever, plus heat. So here, heat is a reactant. And we have the product AB2. So if heat is a reactant, it's the opposite of when heat is a product. So if heat's a reactant here, it is endothermic. And even more split numbers on that, 65%, 35%. 65% said endothermic, 35% said exo. So I'm glad we're going over this. If heat is a reactant, it is endothermic. Overall, the reaction itself is absorbing heat. If heat is a product, that means overall the reaction is producing heat, and that's an exothermic reaction. Okay, now 3 and 4, we're just looking at, we don't have heat written in as a reactant or product, we just have the delta H. The first one, you see that the delta H is negative. It's a negative 503 kcal per mole. Okay, so if it's negative, what does that mean? That means, so what did we get? We got 40, even more split numbers on number 3. This one was almost even, almost 50-50 said endothermic, exothermic. If delta H is negative, what that means, let's go look at our reaction, okay? N2 plus H2 gave us ammonia, and delta H was negative here, okay? The enthalpy of the products was a bigger number, meaning overall heat was released, energy was released. So that's why we wrote in heat, or you could write in, I think we wrote in 20 kcal per mole. In fact, let's go up here and look at it. Right here, here's where we did this one. Delta H was negative, right? That's what we calculated up here. So because it was negative, that meant if you're looking at these numbers right here, the enthalpy of the products was a bigger number than enthalpy of the reactants. And so that gave us a negative delta H. And when delta H is negative, we're going to write the energy term in, or heat, as a product. Okay, so if it's negative and it's a product, that means it is an exothermic reaction. Okay, so 3 right here is exo. Any questions on that?
I did it.
What was that, Hannah?
So I looked at it wrong. So instead of it being like separate from the problem, I read it that was plus.
Oh, that it was written in as a product. Well, you still guessed it right then if you read it as a product. It's exothermic. When delta H is positive, if you'll notice, 3 and 4 are the exact opposite of each other. Here you have A and D make AD, and on 4 we have AD breaking down into A and D. And so the delta H term is the exact opposite, okay? Same number, 503, just positive. And so when it's positive, it's we would write energy in as a reactant, and this is an endothermic reaction. Okay. All right. If your head is swimming, it's okay. You're not alone. I told you chapter 7 was a little intense, and we're just in the thick of it, okay? So we have 5 minutes left. I want to talk about this last slide, and then we'll probably practice this more next week in the lab. I want to look at this reaction because just the same way in chapter 6, we learned to look at a reaction and then create conversion factors with like mole to mole ratio stuff and convert from moles of this to moles of that. We're going to write a conversion factor between moles of a reactant or product, and then the amount of energy that is absorbed or produced in the reaction. Okay, so we're about to create a brand new type of conversion factor and use it in a problem. So if we have a balanced chemical reaction, if you look at this, we have CH4 plus O2 makes carbon dioxide and water. Anybody know what kind of reaction this is? I'm not saying endothermic or exothermic. I'm saying, is it like double displacement, single combustion, combination? Anybody remember? You have a carbohydrate and oxygen, and they make CO2 and water. Yeah, the chat. Sorry, I should stop sharing the results now, shouldn't I? Put that way. Combustion. Thank you. This is a combustion reaction. What do you know about combustion reactions? They're like explosions. Okay. What do you know about an explosion? It usually is
create heat.
Gonna give off heat. Okay. So it makes sense that we see that delta H is negative. It's a negative 213 kcal per mole. So is this endothermic or exothermic? What do y'all think?
Exo?
It is
Would it be
exothermic. Yes, it is exothermic because delta H is negative, and we could write that in as a product. Okay. So if we're looking at this, let's read the question down below. How much heat is released if we do the reaction with 0.35 moles of CH4? Well, in my balanced chemical reaction, I have 1 mole of CH4 reacting with 2 moles of O2, giving us 1 mole of CO2 and 2 moles of water. And this amount of heat, negative 213 kcal per mole, is produced. Okay. So what if we do this, what the question is saying, what if we don't have 1 mole of CH4? What if we have about 1/3 of that? Well, I'm going to go up to my balanced chemical reaction. I'm going to write a relationship because we need a conversion factor between moles of CH4 and energy, which is heat. Okay, that is energy. We need a relationship that relates these two things. So I'm going to write this. Tell me if you agree or disagree. 1 mole from my balanced chemical reaction of CH4 will constitute or give us negative 213 kcals of heat or energy. Okay, that's the relationship from this balanced reaction. So I can actually write that as a conversion factor, right? Just 1 on top, 1 on bottom. 1 mole. See, and we can flip this if we need to. Okay. So this is actually now a conversion factor I'm going to use to do this problem. If I have 0.35 moles of CH4, I want to cancel moles of CH4, and I want to convert to units of heat or energy, which is calories or kilocalories, joules or kilojoules. So I'm going to write this in so that moles of CH4 cancel. So I just created out of thin air almost this conversion factor that I'm now going to plug in. 1 mole of CH4, negative 213, not 113. Okay, and then this is just a one-step conversion problem. You do 0.35 times negative 213. Anybody have that answer for us? Should be like 70-ish. Nobody? I mean, I can do it. Okay, thank you, thank you, thank you. So negative 74.55 kcal. All right. Now this next step, it says, what if we do the reaction with 7.5 grams of CH4? And this is the last thing we're doing. We're at time, I know. We're going to be done after this. What if we do it with 7.5 grams of CH4? Well, we're going to treat it just like the problem above. We just had an added step. First, we need to take grams and convert to moles. Then we can plug this conversion factor in. So how do we go from grams to moles? That's the first thing we need to do. We need to cancel grams of CH4, and we need to convert to moles of CH4. How do we do that? Molar mass. Okay, so we quickly are going to calculate the molar mass of CH4, which would be 12.011 plus 4 times hydrogen, which is, so it'd be 4 times 1.01. And you add all that up and you should get like 16.051, I believe. So first you'll plug in that 16.051 for every 1 mole of CH4. And then to convert to heat, we'll plug in this conversion factor that we had prior. And we're going to cancel moles of CH4 and convert to kcals. All right, you can calculate the answer on your time, but that's all I have for today. Thanks for joining us. I'm going to send a big old class email about stuff for next week. And I'll see y'all in lab, and we'll pick up with lectures next week. Any questions, I'll stick around and answer questions, but I hope you guys have a wonderful weekend.